Everybody survived the blizzard okay? We're actually in luck because we were actually a little bit ahead when it came to our subject material. So we're not like we have to, it's not like we have to make anything up. Okay. I had seen one that I kind of liked the other day. And I thought as a refresher, we might do that one. All right, so here's a Kmap. It is a function of A, B, C, and D, just so that you know what variable names to use. So rather than just having you sit here and do this and or not do it, depending on how you feel this morning, why don't we have a conversation about what the first step is here? Let's start with how do we label this? So right now I haven't labeled any of the important pieces of this, what variables they are, how it's labeled along the top with its numbers. Somebody want to walk me through this and we'll...
Gray code the outer perimeters, 0, 0, 0, 1, 1, 1, 1, 0.
And what do I do? Somebody else, what do I do along the vertical side? Oh, over here? Same thing? 0, 0, 0, 1, 1, 1, 1, 0. Right. What goes for variables here? How should I organize this? Because this is just as important. Somebody else. Yeah. A, B below, C, D. Yeah, we listed alphabetically. We listed in the same order that our function listed as. And the reason we do it that way is because the way we count. We count in binary. So the digit that is farthest to the right is the least significant digit, and the digit the farthest to the left is the most significant digit. That is why when we're looking at things, we label them 0, 1, 3, 2, right? All we have to do to figure out any cell, let's see, somebody pick a cell, tell me which column should I choose this cell out of? Be impulsive, be bold.
2.
2. The second one here. All right, somebody tell me which row. Bold. 3. That's this guy here. So this cell, all I have to do to figure out its min term is look at the row values, 1, 1, append the column values, turn that into a decimal number. What is this decimal number? 7 is incorrect. Those are my place values. 13. Okay, anyway, so that was all extraneous stuff. So we've labeled this off now. So the next question is, what do we circle first? Groups of 16, that's right. How many groups of 16 are there? 0. Okay, there are no groups of 16. What do we do next? Somebody else. Groups of 8. Are there any groups of 8? 1. Where are they?
The bottom 2.
Bottom 2 rows. Right there, okay. Now that is an essential prime implicant. In fact, it's the only implicant of 8. How do we convert this into a term, a min term? Yeah. Find the common value. So we can split it up. We can look here. What are the common values there? A. A is common. Is it a 0 or is it a 1? It's a 1. So if it's a 1, that means we get a positive A. If it was a 0, we'd have A bar. What about what's common to these 4 columns? Is C common? Is D common? Is anything common? No. That's it. That's all it is. It's just A. Okay. Then we circle the rest of the groups of 8 here. What are the rest of what's the next group of 8? There is none. We're done. Okay, so now we're looking at groups of 4. Anybody with a group of, by the way, this is not a group of, oh, you need to see, This is a group of 3. That'll never be a circlable thing. So are there any groups of 4 that have not been circled? That's right, the corners. The corners here. Now, is that okay that we're circling the same things? We can't do that, right? That's not going to work. We've already circled them, right? It's perfectly fine. Why is it perfectly fine? Right, you have to include them, but at least one of this yellow box hasn't been covered yet. It would be wrong to circle like that group of 4 there, because that is entirely circled. There's nothing that's added by that. But we can circle, oh, that's going to be a lot of dashes. Undo. We can circle the outer group of 4 because cell 0 and cell 2, those aren't circled by anything. And it would be wrong, by the way, to circle it as a group of 2 that way. That is just an implicant. It is not a prime implicant, nor is it an essential prime implicant. It's just an implicant because that blue group is fully contained inside of that yellow group. All right, so what is this yellow group? What's in common across the 2 rows? B bar. And across the 2 columns, D bar. Okay, have we circled all of the groupings yet? No. Nope. Are there any more groupings of 4? No. Well, that's not totally true, right? We've seen groups of 4, but they are just implicants. We only ever want to circle prime implicants. So we're done with 4. What about groups of 2? Yeah. This guy right here is a group of 2. Unfortunately, that's the best we can do. There's no cutesy way to make that any better than it already is. So to find that, let's look at it. What do we have in common across the 2 rows? B. And across the single column here, what's in common across that column? Well, the whole thing. So what is this column 0, 1 equate to in terms of literals? C bar D. Yeah, that's it. I like that one. I thought that was a nice fun one. Now, when we last left off, we were talking about video games, as I recall. Right? Why are we talking about video games? Because of the D-pad. And with the D-pad, we said we can't use left and right at the same time. We can't hit up and down at the same time. And that was what we called a don't care condition. A don't care condition says it doesn't really matter if this input combination happens because it should never happen for some other reason. Right? The D-pad, there's a physical reason why you can never press both buttons at the same time. So first let's do it algebraically. We would indicate that something was a don't care in our equation by doing something like this. First off, we keep our sum of min terms terminology. We can say 4, 12, 13, 14, 15. 14. What we'll add in, however, is we'll say summed with, and then the letter D. So this is sum of min terms summed with a don't care condition of, for example, that. So when you see this, sum of min terms mean that there's a 1 in that cell. The D means a don't care. When we create our Kmap, not the straightest lines I've ever drawn, it'll be relatively simple here to fill this in. Cells 4, 8, 9, 10, 11, 12, 13, 14, and 15 are 1s. The don't care values, which I'll fill in with an X, are 0, 5, and 8. Now, everything else is a 0. So the don't cares add a new symbol here. don't care. A don't care can be 0 or it can be 1. It's up to you as the designer. Now here's where things get interesting. Our rules are still the same. We circle groups of 1s in either 16 or 8 or 4 or 2 until there are no 1s left uncircled, and we're always looking for prime implicants whenever possible, and we want to reduce the amount of overlap. So I think it's pretty easy to see that this is a nice group of 4 to circle, right? There are no groups of 16, there are no groups of 8. That's a nice group of 4 to circle. It circles all the 1s. And this would be AB. That's the term. Now, we have a choice now of what we can circle. There's only one cell that has a 1 in it. Without these don't cares, we'd be forced to rely on this grouping of 2, which would end up being something like B, C bar, D bar. With don't cares, however, we can choose to treat any of these x's as if they were 1s. So what I'm going to do, I'm going to circle this vertical space here. I seem to be having a lot of trouble right on this part right here, making it straight lines. And this cell will just be C bar, D bar. Right? If you look at the gray code, A, B, C, and D. What this means now is if I were to build this circuit, anytime I put in 0, 0, 0, 0, which corresponds to this cell here, I'd get an output of a 1, which is fine because I don't care what the outcome is in this cell. I don't care. Could be 0, could be 1. If I were to put in a 0, 1, 0, 1, that corresponds to this cell here. What would the output be for this equation if I put in a 0, 1, 0, 1 for A, B, C, and D? Would it be a 0, a 1, or something else? All right, let's do this. Everybody raise your hands. Put your hand down if you think it's going to be a 1. Put your hand down if you think it's going to be a 0. Nobody thinks it's going to be something else? Okay. In this case, well done. It's not going to be something else. It has to be a 0 or a 1. But in this case, it's going to be a 0. I'll prove it to you, right? This is my equation. So let's just do the binary arithmetic. A is 0. B is 1. ORed with C bar, which would be a 1, ANDed with D bar, which would be a 0. So what is 0 and 1? 0. What is 1 and 0? 0. What is 0 or 0? 0. So it's going to be a 0. Now, I could have told you that visually looking at this. We didn't circle it. If we don't circle it, it's going to be a 0. Okay? Now, that's not the only way I could have solved this. I could have, and I'm going to need a little more space here, so let's clear this out. Instead of circling that vertical grouping there, I could have just as easily circled this group of 4. That would have given me the following. I'd still have A and B, but now I would have B ANDed with C bar. In this case, if I put in a 0, 1, 0, 1, I get out a 1. But if I put in a 0, 0, 0, 0, which would be that cell there, I'd get a 0. Don't cares give us a lot of options because we can choose whether or not to circle them, only if it helps us make larger prime implicants. Okay? Let's try another version of this. I'll give you another Kmap in an easier to see color. And now I'm going to tell you, let's see. Don't care, 1, 1, don't care, 0, don't care, 0, 0, 1. Shucks, I messed that up. Starting over. Hold on. Sorry, guys. Let's try that again. Don't care, 1, 1, don't care, 0, don't care, 1, 0, 0, 0, 1, don't care, and finally 0, 0, 1, 0. A, B, C, and D. Now, I think at this point you could circle the ones and tell me what the sum of product solution is, but what if I asked for it simplified in product of sum notation? Before we inserted don't cares into the mix, how did you find a product of sum representation? What was the thing that you had to do instead of, yeah, circled the zeros. And we do the same thing with don't cares, only now what we want to look at is using the x's as zeros. So without the don't cares, what would I have been forced to do? I could have circled that group of 4 there, and let's see, this group of 4 here, and then probably that group of 4 there. You don't have to write that down, but that's what I've had to do. So I would have had 1, 2, 3 terms. Instead, though, I've got these don't cares, which affords me an interesting opportunity. Remember, we start looking for groups of 16, then 8, then 4, then 2, then 1. There's obviously not a group of 16 zeros, but with don't cares, there is a group of 8 zeros. Okay, and that would be the letter D bar. That's our term. We still have 2 zeros left to circle. What would we end up with there? So would we have to circle that group of 2? Or is there a better way? We cannot circle this group of 3. That's not a valid thing to circle. It has to be a power of 2. So if we can't go vertical, can we widen the net a different way? A group of 4, where? Yeah, we can take this group as a 2 by 2 square. And that 2 by 2 square would have A in common and C bar in common. This, by the way, however, is not product of sum. Remember, what we just did was we circled what F wasn't. So if we invert both sides, we'll end up with F is equal to, by applying De Morgan's law, D ANDed with A NAND C bar, which we can apply De Morgan's law to again and get A bar or C. That is a product of sum representation. That's where you should stop for a product of sum. Yes, it is possible that you could expand this out and get A bar D or CD, but this is a sum of product, which is not what we asked for. We wanted product of sum. So we're actually doing okay here. Now, all of these Kmap tricks have been about finding a standard sum of product or a standard product of some term. That will always reduce, in the case of sum of product, to some number of AND gates going into a single OR gate. Some number of inputs on the AND gates might even be a single input. If you have a single input AND gate, that's really just a wire, okay? And that's actually what we had just a second ago. We had an example of a term that was just a single literal. So that would be a sum of products representation. If you swapped these, you could also have AND gates, and these would be OR gates. If you were doing a product of sums, okay, either way, you'd end up with this. Now, this is not always optimal, and in fact, the more inputs into this OR gate that you end up with, the less optimal your circuit is going to be. I'm not going to go into why it has to do with the parasitic capacitance inside of multi. Dr. Rancor, in his 311 class, will go over this with you quite thoroughly. Needless to say, the more inputs on a gate, the longer the propagation time, the larger the propagation time. So in a lot of ways, it's better to do a multi-level optimization. And before I go too much farther, I just want to back up a little bit here and do some rules. So we have to have a goal in mind when we're optimizing. So I'm going to give you some cost criteria. That is so not how you spell that. IA. There we go. Criteria. As to how we evaluate how costly a circuit is going to be. And generally, we're looking at either time cost or space cost. So let's take a function here as an example. Okay, this is not a standard sum of product or product of sum. When we implement this, how are we going to go about doing this? Well, we've got this OR gate here, and on one side of the OR gate, we have an AND gate with A and B. Fine, cool. On the other side, we have an AND gate. One side has C bar. The other side has D ORed with E. So when we look at the delay, we look for the longest delay path. Basically, how many gates can I go through from output to one of these inputs? So if I follow the top branch, that's a gate delay of 2 gates. If I follow it through this way, that's a delay of 3 gates. And the last way I can go through here is also 3 gates. So that's one way of measuring delay. Based on time. We can also look at it based on space. So that's time. In gate delay. Another way is space, where we look at the number of inputs. Because all things being equal, every input needs two FETs or two complementary gates. So let's count up the number of inputs. So on this, I've got two inputs. Here, this inverter has a single input. This OR gate has two inputs. This AND gate has two inputs. This OR gate has two inputs. So all told, 1, 2, 3, 4, 5, 6, 7, 8, 9 inputs. Okay. So we've got, in the case of time delay, 3 gate delays. In the case of space, we've got 9 inputs. The last way of looking at this is kind of space related. It's the number of literals. And in this case, we have 1, 2, 3, 4, 5 literals. This is how you would evaluate any function for its cost. And you can choose which criteria you're going to use to justify that your way is the best way. And it really depends on your project, what's going on. You might have a limitation on space, so you want to reduce the number of inputs. Okay, so it might be better off to combine this in some way to reduce the number of inputs. You might want this to be really fast, so you have to reduce the number of delay stages, which you can do. Okay, now how does this deal with multi-level optimization? Well, there's 2 tools you're going to use in multi-level optimization. One is factoring, which is pretty familiar to you from algebra and various other things. The other is decomposition. Okay. What connotation does decomposition usually have? When I say decomposition, what's the first place you think of or the first idea you think of? No, factoring is factoring. Decay, yeah. Death. I don't really think of simplification when I go to decomposition. No, I think of dead bodies. Maybe that's just me. I watch a lot of like CSI shows and murder mysteries. Decomposition. Decomposition is when a body rots. How does this have anything to do with digital logic? Decomposition is breaking down into base elements. We turn back into dirt. That's decomposition. Okay, let's take an approach where we'll just use these tools and look at what they get us. Okay, those are our 2 tools. Let's take a function g, and we're going to list it out by its min terms. ABC or ABD or E or ACF or ADF. Now this is, in fact, a 5-input circuit. It's got A, B, C, D, and E as inputs. Now these aren't just min terms, right? Because E all by itself corresponds to like 16 min terms. But rather than list them out as min terms, we can do it like that. This is how we're starting. This is what we're given. And what we'd like to do just for this one is let's reduce our gate input cost. Now our gate input cost is how many inputs do we have? And we can look at this. First off, we want to look at all of our terms. In our terms, the number of gate inputs is the literals. So for this term, we've got 2 gate inputs. For this term, we've got 3. Here it's just 1. Or we could say 0 because there's no gate involved. Here we've got 3. Here we've got 3. So let's write that down. 3, 3, 0, 3, and 2. there's more to this gate input cost because each term itself adds an additional gate input because we have it going into a giant OR gate. So all told, our gate input cost is 5, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. So first thing we can do to reduce our gate input cost is factor things. We want to remove duplicates across multiple things here. So let's factor this out. Oh, I didn't write this all the way down. That should be C. So that's actually 3, which means this is 17. That's ABC, ABD, E, ACF, ADF. So when we start factoring, we look for subterms inside of our terms that are the same. And the first one I see is right here. AB is in both of these terms. And let's see, across other terms, are there any other things in common to some of the other terms? The
last two have A.
The last two have A. That's absolutely right. Yes?
Do they have AF?
And that's true as well. They have AF. So it's better to factor larger groups. So you could factor A out of this, but they'd still have F in common. So the term we're going to factor out of those two is AF. How would we do this? Well, we factor out an AB. And we look at what's left in that term, that's just a C. We look at what's left in the next term, that's just D. All right, E we are not factoring anything out of right now. And here we know that we're factoring out an AF. If we factor out an AF of the first term, that leaves us with C. If we factor an AF out of the second term, that gives us D. All right. Now, depending on how we want to do things here. Did I do that correctly? I think so. CF. CD. CD. Yeah. All right. We can continue to factor as many times as we want until there's no more factoring possible. So what can we see that's in common to at least one of these terms? Or at least two of these terms, rather. Yes? CD now is actually, it's in both of, that's not the color I wanted, green. CD is in both of these terms. So, and it's C or D, right? Is there any way we could increase that? Is there anything that is also in common to those two terms? A is in common to both of these terms. So when we factor this out, we're going to factor out an A ANDed with C or D. And that's going to give us, and I'll use square brackets here just so that we don't get confused. What's left in the first term here? Yeah, B is left. So we'll factor out a B there. These terms are ORed together. So what's in the final term here after we factor out an A, C, or D? F. And it's important to remember that we still have E. Okay, so now looking at this, let's evaluate our gate input cost. It gets a little bit trickier. I'm going to draw it out just so that we can kind of see easily here. We've got this OR E. We're ORing that with everything else. And what is that everything else? Well, it's a 3-input AND gate because we have 3 parts here. The first part is pretty simple. It's just A. Second part is an OR gate. And that is C ORed with D. Final part here is, what's left? B or F. Same equivalent function. Let's look at its gate input cost. 1, 2, 3, 4, 5, 6, 7, 8, 9. So our new gate input cost, GIC, is 9. We've gone from 17 gate inputs to 9 gate inputs. That reduces our size quite dramatically. Okay. It also reduces the complexity of our circuit. If you look up above at G, we had 1, 2, 3, 4, 5 terms. That's a 5-input OR gate. That is about as slow as it gets. Okay, here our largest gate is this AND gate with 3 inputs. Now, I don't know if you've noticed yet, in the 7400 series, we've got a 7400. That's a 2-input NAND. We've got a 7410, which are 3-input NANDs, and we have a 7420, which is a 4-input NAND. I think there might be a 7430, which is a 5-input NAND, but I'm not sure about that. But generally, if we can keep things under 4, we're in pretty good shape. So that's one way of reducing this, using just factoring. That's one tool in our arsenal. Okay. By way of example, let's look at another for decomposition. Decomposition is the harder one. Factoring makes a lot of sense. We've done it in algebra for years. Let's take another equation here, G equals, and we're just kind of making this one up. We don't know what this really is involved in or what this circuit is supposed to do, but we can write it out here, A D bar or E or F or, oh, hold on, nope, try again. I'll get there, I promise. Okay, A, C, sorry guys. A, C bar, E, or A, C bar, F, or A, D bar, E, yep, or A, D bar, F, or B, C, D, E bar, oh, I'm just going to be able to fit it, E, F bar. Okay, I squeezed it in there just a little bit. So that's B, C, D, E bar, F bar. What is our initial gate input cost? What? Well, we can count it out. So that's 1, 2, 3, 4, 5, 6. Or rather, I should say 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5. That's not the whole story, because in this first term here, we have A, E, then we've got an inverter here for C. So actually, we have to add on an additional for every inverter we see. And here we've got 2 inverters, so that's 2. So that's for each of our terms. And then we also have an additional OR gate here, so we count up the number of terms. 1, 2, you can't see that. 1, 2, 3, 4, 5 extra terms, so we'll add on 5 there. So what do we end up with? 4, 8, 12, 16. 16 plus 5 is 21, plus 7 is 28. Is our gate input cost. So that's where we're starting. So it's we can only go down from here. And to do that, first off, we're going to look by factoring, because the first step in decomposition is actually factoring out. So what things do we have in common across these terms? Oh goodness, well, let's look. In the case of the first 2 terms, I see actually an AC. Let's start there. Or rather AC bar, which gives us an E or F. In the second 2 terms, I see AD bar in both, so I'll take AD bar out, and that leaves me with an E or F. I think we can see maybe that some other things are going to happen here. Let's see. Can I factor anything out of the final term? No. I don't see anything in the final term that'll really help me there. Nothing quite so easy there. So I'll write that down. That'll be our first level of factoring. B, C, D, E bar, F bar. Already we've reduced our gate input cost by a bit. We can continue to factor though, because what is in common to the first two terms?
A, E, or F.
Yeah, so the term that we're looking for is A and E or F. So we'll factor that out. A and E or F. Factoring that out of the first term gives us a C bar. Out of the second term gives us D bar. B, C, D, E bar, F bar. That's about as far as we can go with factoring. And if we didn't know any better, this would be as far as we could go. And we could look at this gate input cost 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I think we get to 19 there. And that's as best we could do. Here's where we need to get a little crafty. We get crafty by looking at decomposition. And decomposition, we're going to be relying heavily on my favorite law, De Morgan's law. What does De Morgan's law say? It says that if we have A and B, or A NAND B, that's the same as saying A bar or B bar. And if we have A NOR B, that's the same as saying A bar ANDed with B bar. We want to look for something that could have been De Morganed. So right here I see C and D, or sorry, I see C bar or D bar. C bar or D bar could have been C, D inverted, C NAND D. Now we don't have C NAND D anywhere in here, do we? No. But here's where decomposition gets a little crafty. Let's say that we're going to create a temporary variable called X. We can even say X1. X is going to be equal to C bar or D bar. If that's true, then X1 bar, or rather X1 bar, is equal to C NAND D. Everybody okay with that? All right. So let's say we apply this. A and E or F. And we're just going to call this X1 now. Over here, I've got B, and then I've got CD, which is exactly what we have here, except it's inverted. So I'm going to call this one X1 bar, because together, these are the same thing. Remember, by applying De Morgan's law, we're in good shape. So that is X1. This is X1 bar. And then we still have E bar, F bar. By doing this, we have effectively just added an inverter into our circuit, and we're reusing the output of this OR gate. We're continuing to decompose. Now, there's actually one more decomposition. Can anybody spot the decomposition that we can perform? In the back? Yep. Don't say plus. Say OR, yeah. E or F. So let's create another variable here, X2, and let's call it E or, oh, hold on. Let's erase that. I don't want you to think that this, oops. I don't want you to think that this has anything to do with inversions here. E or F. What would x2 bar be? Well, if we inverted that, we could apply De Morgan's law, and we'd end up with E bar ANDed with F bar, which we do, in fact, have. So putting this together, we'd have A ANDed with x2, x1, ORed with, let's see, B, x1 bar, x2 bar. Whew. There is no hard and fast rule for how you decompose. Okay? You have to search for those decomposition terms. Generally, you're looking for things where you have, terms that are ORed, and then somewhere else they're inverted and ANDed. Or you could look at it the other way. You could look at terms that are ANDed, and then somewhere else they're ORed and inverted. So what does this actually end up looking like? Well, let me take that whole equation here. Go to a new page, and we'll paste it in. This is the equation that we came up with. A ANDed with x1, x2, or B ANDed with x1 bar, x2 bar. As a reminder, x1 was equal to C bar or D bar. X2 we made equal to E or F. So how do we build this? Well, to start with, we've got an OR gate, but it's only a 2-input OR gate. Going into this, we have 3-input AND gates, A, and then we've got x1 and x2. I'm not going to draw those just yet, but down here we have B, and then x1 and x2 bar. So I've got inverters here. So then I've got to build x1 and x2. x1 looks like this, C, D. So I can take x1, and let's do it in green here just to make things make sense. Goes there, and there. I'm going to go off on a bit of a tangent here about drawing schematics. Depending on where you learn schematics, sometimes if you have to cross a wire, you'll see people do something like that to indicate that there is a hop over the wire. Other people will just draw a line straight through. This is my preferred way. Don't do that. No, 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 no. It just clutters the drawing. What you should do instead is indicate explicitly anytime there's actually a, anytime there is an explicit connection with what we call a junction. Just put a big dot there to indicate that it's connected. All right, finishing this off because I know we're running short on time. E or F, and I'll do that guy in red, like so. So all told, our gate input cost, our new gate input cost is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What was it previously? 19. So we've still gone down. This is not the most reduced. Stick with me for just 1 minute and I'll show you why. Our decomposition was chosen in haste. If I had instead chosen x1 to be CD bar, okay, I could have still used the same decomposition, but I would have changed ever so slightly how I built this. The reason I wanted to swap these, I should have used them in opposite terms, is whatever your function that you're decomposing is, you want that to have the minimum gate input cost. So the gate input cost just for x1, look at it, 1, 2, 3, 4. If I had instead done this, it would have been 2. So the better way to do this would have not been to use that version, but use this version. The difference in what you would do here is you would add an inverter there. So this would go straight through, and then it would be inverted there. Does everybody see the difference between the two things, the two implementation ways? So that one would have reduced our gate input cost from 16 down to 14. Okay? So when you're decomposing, choose your sub-function, x1, x2, so that it has the least gate input cost. The reason we're learning about multi-level optimization, because it is multi-level, right? We're adding delay stages, is because this is how you want to implement things on a chocolate bar, on a breadboard for your circuits. Reduce the overall number of gate inputs. That also tends to reduce the total number of chips and reduce the size of the chips. So there we are on multi-level implementations. Okay. Nothing has changed about lab. Lab still happens normally. We are... Anytime that I have an open office hour, I will open the lab for a makeup lab. However, there are makeup labs. There's a makeup lab I know today at, what did I say, 3 to 4? 3 to 4, 218 will be open for makeup. Okay?